Good evening, ladies and gentlemen. It's my pleasure to start this new section of electrical engineering. We have 5 presenters here today, and one is missing, unfortunately, but still the presentation time is 15 minutes together with questions. So please keep the schedule about 10 to talk about 10 to 12 minutes and when answers to the questions, and otherwise we will miss this evening dinner soon. So our first presenter comes from Serbia, Nebojša Kjevalcha. His topic is linearization approach for symmetric hysteresis loop modeling and call-loss prediction. The floor is yours, please.
Thank you, Mr. Chairman, dear colleagues. Let me start with our presentation. Generally, this is the content of our presentation. First, we will give a few words about motivation for this complete research, and we will go through the general linearization approach. We will continue with most important topic regarding linearization. This is the approximation error and its distribution as the most important part which defines the, let's say, the quality of the linearization approach which is used. And we will also give the experimental results of our linearization regarding symmetric hysteresis loop curves, which are the topic of this research. And finally, we will do some prediction of generally arbitrary inner symmetric hysteresis loop curves. And finally, we will try to conclude. Generally, when we are talking about the relation between magnetomotive force or magnetizing current and the magnetic flux, we are typically talking about 2 types of materials. If we have non-magnetic material, in that case, mainly we have purely linear relation between H and B. While on the other hand, if we are talking about ferromagnetic materials, we can recognize here typical hysteresis curve, which is practically almost always used, especially in the power transformation and distribution systems in electrical domain. When we are talking about linearization of the BH curve for the ferromagnetic materials, the most important points are let's say the corner points of the BH curve, and also the very important is the shape and the size of the hysteretic area. This is the area inside of the BH curve. What is very significant to say, the position of those corner points are when we increase excitation in such materials, which means when we increase magnetizing current, the trajectory of those corner points are absolutely not linear. So we are stretching the hysteresis curve, but the trajectory of the corners is not linear function. Also, the shape and the size of the hysteresis loop is again non-linear. And those are the challenges which we try to give one solution. Generally, concerning the modeling of the hysteresis curve, for that purpose, there are typically 2 approaches. The one approach is to use as the argument electrical angle, and if you use the electrical angle as the x-axis argument, we can create a graph of the magnetic flux. This is the black line, or we can also put on the same graph excitation current, which is the gray one. And we see that we have slightly nonlinear curves here. Other approach is to use as the argument magnetic flux. In that case, of course, magnetic flux is just the mapped 1-to-1. And again, if we are thinking about in this approach, creating and analyzing excitation current, we see that we have again nonlinear function, but somehow shape is more or less simpler. Generally, we decided to use interpolation and we have analyzed interpolation over the Chebyshev nodes of the first and the second kind, and we will give the motivation why. The first on we did analysis over the electrical angle domain, and we also used the analysis over the normalized magnetic flux domain. So we will continue our discussion about argument of normalized magnetic function. What we see here, we see the graph of the algebraic interpolation polynomial over 10 Chebyshev nodes of the first kind in the normalized magnetic flux domain. What do we see? We see that we have the relatively higher distribution of the points around the zero, while around the extrema and the corners of the domain we do not have the good coverage of the points. For that purpose, we have introduced Chebyshev nodes of the second kind, which tend to be pretty optimal for this type of problem, because we have again relatively high density of the points around the zero, and we have also the very good coverage of the corners. We have the higher density of the nodes, which is very important because, as we have mentioned on the very beginning, we do have a problem with nonlinearity of the curve itself. So if we use this approach with the Chebyshev nodes, and if we apply the same the linearization approach for the rising curve and for the falling curve, we can accomplish and we can linearize complete hysteresis curve, rising and the falling edge, as we can see on these two graphs. So now for the characterization and evaluation of the quality of the linearization that we have used, we have plotted here the error distribution functions, and we see here the error distribution function for the Chebyshev nodes of the first kind, and we see the similar on the same graph the error distribution function for the Chebyshev nodes of the second kind. What do we see here on the left graph? It's difficult to say which one is better, but generally the very significant point is that if we look at the Chebyshev nodes of the second kind on the edges of the domain, which means in this point and in this point, the function has the value of 0, while the error distribution function does not have 0 on the corners of the domain. And this can be easily spotted here on the right graph, where we developed practically modulation function for those two approximations, and we see that for the Chebyshev nodes of the second kind, which is the black line, we see practically that there is like an envelope for this sinusoidal error distribution shape. So we see that on the edges, of the domain that the error decreases, which is practically most important achievement of this research. Okay, here still we see some additional analysis of the errors depending on the number of nodes for the Chebyshev approximation, and we see, for example, for the 26 nodes for the Chebyshev function, we see that error is really practically superior, pretty suppressed. What is another very important part? It's a very important part that when we are using this approach, it's very significant to decompose the original hysteresis function into its hysteretic and unhysteretic component, and just give me a few seconds to describe what that means. As we have seen on one of the first slides, the shape of the hysteresis curve, we could decompose each of them into purely hysteretic part. This is the one which is painted here in black, and this part is exactly difference between the rising part and the falling part of the hysteresis function. Okay, and this is it. And on the other hand, the other component which stays, this is so-called unhysteretic component. This is component which is practically the average value. If we find the average value, if we sum both curves and divide by 2, we are getting the curve which is exactly unhysteretic. Why unhysteretic? Because this what we have is a real function, which means for each value of the argument we have only one point of function, and the hysteretic component tells us just the difference between rising and falling part. And this is the main idea about this the composition which is used. Here is the result of our approximation, which is applied to strictly hysteretic part with 21 Chebyshev nodes of the second kind. The gray curves are the experimental curves from the lab, while the black dotted are interpolated. And we can see that the distribution and the shape of curve is pretty matched. And finally, as a conclusion, we can say that interpolated prediction of an inner symmetric hysteresis loop curve requires that all measured curves have to be decomposed. So before decomposition, we have to decompose curve into hysteretic and unhysteretic component, and then each of the components should be interpolated through this procedure that we have seen. And finally, sum of both approximated curves gives the complete model, which pretty successfully models hysteresis curve in the ferromagnetic material. So this is, in short, I'm ready for questions. Thank you.
Thank you. It's now time for questions. Questions, please. Yeah.
Just because it is quite nice mathematical model, have you implemented it somewhere or check how it does improve something in, I don't know, transformers analysis or whatever?
Thank you for question. Yes, we did, and oops, just a second. Yes, these curves are taken from the lab, from the transformer, which is defined on the silicon steel M4 material, and these are the results taken from the lab. So this approach with the composition gives really good behavior, because in let's say in related work which can be seen in these days in the other scientific conferences and journals, this decomposition is not so used. So typically people are trying to completely linearize just, let's say, the rising and the falling curve of the hysteresis phenomenon, which from our point of view is not so optimal, because we are talking about two, let's say, when we are talking about hysteresis, it in reality keeps those two phenomena. One is the unhysteretic part, which is like if we assume that hysteresis is very, very narrow, almost zero, and we are just analyzing the path of the trajectory of the left corner and the right corner. This is one phenomenon, and another one is the change in between the upper and the lower curve, which is another phenomenon, which in reality exists in the hysteresis. So we decided to separate those two, and with that approach we are trying to cover it in the better way, hopefully. Thank you.
More questions, please? Yeah, I had actually similar questions. So, yeah, I will add some. What is a practical value of these approximation or this calculation? What it gives in practice?
In practice, it could be used for the simulations, typically for the simulations and evaluation of the behavior of the magnetic materials.
For design purposes of transformers.
Yes. But it's in general in the most of the tools, for example, like for the FEM simulation tools and SAR tools, most of them are offering extremely simple model of hysteresis. But especially for the loss prediction, it's very, very important to include this nonlinearity, which we can see here. So for the let's say high end the simulation tools, it's really important to have the model which successfully models especially because of the loss predictions.
Okay, thank you very much.
Thank you.
Now we go to second presentation. It will be presented by Xin Wang from China, and the topic is Maxwell equation-based on mining transient electromagnetic method for coal mine disaster water detection.
Thank you, Chairman, and good afternoon, everyone. It's my great pleasure to do the presentation, but this is not for me. It's for the some professor from it's the professor from China also, and he has some problem. He can't come here, so I do some presentation for him. And if you have some questions, you can send him some email. In the end of this PowerPoint, there has the email. So let me start, because I'm not the professor for this area. So I will say in some sentence. And now we can see this is the outline of this presentation. It includes 5 parts: introduction, principle of the testing method, numerical simulation, application in the field, and at the end of it, conclusions. In this you can see this is the map of China. Yes, and this is in this map we can see the distribution of the hydrogeology of the hydrogeology mining in distribute in China. The color is meaning the dark color meaning the problem is much more. The problem is much more hazard than others. So you can see in the north of China, in this part of China, and in the middle of China, the hydrogeology mining is very. There has a lot of like this, and in this picture. We can see this is workers working in the mining, and we can see for this picture it's very difficult to find. There has some hazard will happening in this part, and. And in this slide, it is the water inrush hazard. So the pressure of the water is very high. So if this disaster was happening, it will be a very terrible thing for the miner lives. In this table shows the accident which happened in the coal mining, and from this part is the number of the accident. This is year. This is the number of accident, and this is the death of people. Number of deaths of people. So it's a very terrible. In this paper, Professor Ben Yu used a method to detect the hidden of the inrush water. So in order to solving this problem, firstly, problems of mining water inrush, they use a method which named MTEM to solve these problems. And MTEM, and this is in this part. It's the roadway. It shows the roadway in the miner, and for this part, it shows the second. In this part, it shows the way which the way of the electromagnetic method to transport, and for this direction of the detecting. So this is the method of he used, and he used the principle of MTEM. He used Maxwell equation to do this work, and in this part is the theory of which he used. Yeah. And for the detection, he used vertical component of coil, and it can transfer into the resistivity with these equations. And this in this part is the numerical simulation. Numerical simulations, and it can from this part we can see this in these colors is meaning the distribution of the resistivity. And he also do some real testing detection in Shanxi province in some mining. This is the picture of he testing. And for this picture, for this part, you can see the really testing result of his work. And the work this detecting was also be verified by another testing method. So it's the conclusions. Firstly, he used a new application method method to detect in a coal mine roadway, and then the numerical modeling and the modeling result match the geological model reasonably well. He also do a lot of real text in Shanxi province, and the present method can be feasible and effective applied in the disaster water source detection in coal mine roadway. Okay, thank you.
And thank you for very interesting presentation. As much I understood that you were not answering the questions. Yes. Is it so? So yeah, I just maybe pass one question to the author, and I'm interested how some other materials influence these results. Like this is intended for detection of water, but if there are some other particles inside the coal, like maybe some metal particles or other that are not water, how can you separate these results? When is it so?
Yeah, yes, that maybe yes, it's a very good question. Yeah. But I'm so sorry for this because I'm not working for this area.
Okay.
So, but I will ask Ben Yu for these questions. Yeah. Okay.
Thank you very much, then.
Yeah, thank you.
And the next presenter comes from Turkey. It's Mustafa Seker, and his presentation will be about an experimental approach for understanding voltage current characteristics of electric arc furnace load.
Hello everyone. We are experimentally try to understanding of VI characteristic of electric arc furnace load, and my name is Mustafa Şeker, and Arif Mehmedov is my supervisor, professor. And when we look the content of the presentation, firstly, aim and scope of work, introduction, electrical system of electric arc furnace and experimental study, and how we made a model for electric arc furnace and simulation results will be concluded. Our aim and scope. Electric arc furnace non-linear, very complex loads and changing very fastly. So we cannot understand it very well. So that we need to determine it with experimentally approach. And when we look at the literature, we can see that so much characteristical model for arc furnace load. For example, VI characteristic, I used the VI characteristic in this work. Exponential model, hyperbolical model, like that, and Casimir differential equation like that. So much approach we can see that in literature, but I tried to experimentally define it, because if we can create a model for electrical arc, we can make good analysis in the computer, because these applications is very high costly, and if we can model it electrical arc, we can analyze it in the computer. For that, I measured current and voltage waveform for power quality analyzer, and I defined a new model with MATLAB Simulink. We can see that here, very complex and very fast changing. Arc furnace is generally have 4 characteristics. First manner, charge and boring. In this period, we can see that changing very fastly, and in the melting period, when we compare with charge and boring, little good. But in the refining period, we can see that so much fluctuation when we compare with this other period. So when we look at the systems, we have high voltage bus bar and middle voltage bus bar, and we have 2 transformers in systems feeding the electrical arc furnace load, and we have harmonic filter groups and static var compensation groups. In my works, facility didn't allow to me harmonic filter out of order, out of the systems. I measured only these systems is on, and it's a single line diagram. I used that single line diagram, and according to this parameter, I can make some single line diagram for one phase. And in here I modeled the harmonic filter groups and electrical arc load. I said that we have 4 manner in the working, and for this analysis I used Hioki power quality analyzer, and I obtained the current and voltage characteristic of electrical system. And I used this characteristic, and I find the arc current and voltage graphics. And when we look to these graphs, we can see that system is very complex, and it's very hard to modeling of this characteristic. So in literature, generally using this this equation, but it is very complex and it's so very hard. So that I determined this characteristic for four region, and area 1, area 2, area 3, area 4. And when we look at the condition, current bigger than 0, voltage bigger than 0, and deviation bigger, we can determine this characteristic. And when we use it to curve fittings, MATLAB curve fittings, we can explain with this characteristic and this equation. But this polynomial equation we can determine, but it is so it's a big problem for us, because I will explain in a few later. And when we look to this area, we can determine the equation and 30-degree polynomial. But electrical system have a flicker effect, so that I must to add this system the flicker. But when I add the flicker, this polynomial equation very complex, and these solves are very hard. So that I determined a system, and I measured the power for electrical arc, and approximately these megawatt systems have reactive power, active power, sorry, and I defined a transfer function. We have a transfer function and function block. This function block is determined to this characteristic, and I add the flicker effect, this model. And when I work at it, I find a characteristical graphs. When we look at these graphs, if we are using this MATLAB model, we don't need to solve the polynomial equation, and we can explain it basically. And when we add the flicker effect, we can find this characteristic. And when we compare it measurement and simulation result for electrical arc, we can see that our model is nearly same with experimental characteristic. And with this model, we can compare to experimental and simulation results. Total harmonic distortion is very near. I tried to different model too in this work, and this model is explain our characteristic is very well. And when compare the literature, this model is very giving the very good result according to others. We can say that as a result, we can say that we have this VI characteristic with MATLAB. We don't need to polynomial equation, and we can describe the basic very easy to flicker effect. And if we can change the parameters in the model, we can use it for other electrical arc furnace loads. And this model could be explained how is working the electrical arc furnace, and computer aided design. With computer aided design, we can understand the power quality for new systems or available systems. Thank you.
for questions. Please ask. Okay.
Usually when you use some model, you use the model for some purposes.
Yes.
And what you presented is just the general searching for pattern in your, let's say, heuristic approach to the problem of this.
Yes.
Where do you plan to use this model? Because, you know, sometimes your model must consist of these features or another. So,
Yeah,
so usually
yes.
this model is not just for modeling, but it's for using some.
Yes, this model for only I use it for only single line, but in my future works it's not including here. I made to three-phase complete model for electric arc furnace load, and I compared experimental and simulation result with other models. And this model is given the best presentation to when we compare to others model in literature.
But do you use
Yeah.
it to control something, or because usually you want to control something, you need model
Yes.
to control something, so you can use the model for some control
Yes.
purposes.
In this paper, you know, I cannot add everything here. So I added some parts of my works, and actually I have active power, reactive power changes, voltage fluctuation, flicker effect. All is I try to investigate it to all, and only it is some parts of my works. But I can say that when we compare the other models and when we investigated the three-phase load, it's given the very best solution for when we compare the other models.
Thank you. And I have one more question similar to my previous one. Did you do some practical experiments or collected some practical data? How good it fits with these modeling results? How well it fits your modeling? How
Yes.
well it fits with real practical measurement data?
I can say practically I measured it and I obtained it already. And my model is when we work the model very near to a real result, and I can say voltage fluctuation and current and power and active power and total harmonic distortion given the best result.
Okay. And the second question from me, how dangerous these disturbances actually are that are coming from this arc furnace load?
Yes.
Are they dangerous to some other equipment or not?
Arc furnace load, because they are changing very fast, and it's this 16 MVA loads, but if we change the parameters, we can adopt it for other arc furnace.
Okay, okay, okay. And thank you. Are there more questions? Yes, please.
Generally, just arc itself, as we have seen on one of your slides, that practically almost the voltage and the current are in the phase. Is this typical for the arc, or have you spotted some inductive component? Can you tell us something about that?
Yes. Arc furnace already have very inductive power, and how I can say.
Maybe if you can just give us the slide with voltage and current. Yes.
This.
Yeah.
Yes. And it's changing very fastly. I can explain it in this figure. I will come here. And actually, arc furnace have interesting this part. We have four working process, and electrodes is scribing the metal, and when we using the arc, metal is melting. But we have so much parameter here, because if we chose to arc from electrical arc length stable, we will not see that flicker effect. But it's not possible, because this melting metal, it's not stable, always moving, and I can say yes, and this arc is not always stable. So this we can see here very fast changing. We are see that in the network.
Thank you. And yes. And as much I understood, the next presenter will be the same. Oh, no. Since I understood that one presenter is missing, and then the next will be power quality measurement and analysis in electric arc furnace of Turkish electricity transmission system. And the presenter is also Mr. Masek. Please. You are next, because one presenter is missing.
Oh, missing. Okay.
Yeah.
No break.
No rest.
No rest.
Actually, it's nearly same with other people. It's modeling. This is the analysis, experimental results. Power quality measurement and analysis in electric arc furnace for Turkish electricity transmission systems, and aim and scope, interaction, electric arc furnace system, experimental research, and EMTP analysis and simulation results and solution offers we will present it. The aim of the scope, we said that electrical system arc furnace is very nonlinear loads and have a big problem for electrical systems. In this study, we are experimentally measured to electric arc furnace loads power quality, and we tried some suggestion for improving the electrical arc furnace loads damage. When we compare the last year, Turkey have a very fast development in arc furnace production. Today in Turkey, more than 70% of the steel is produced with electrical arc furnace, and this is a very big rate for total power. I used the three analyzer, Chebyshev, Arnox, and Hyoke, and Sivas Iron and Steel Incorporated Company. We are connected to this power quality analyzer according to AIC standards. We can see that, and here we are connected to analyzer, and we see that before this section, it's very complex and very fast changing. But when we compare the changing in melting process, we can see that similar characteristic. So that I investigated some melting period, nearly 18 minutes, and we can see here charge manner and melting and refining process and active and reactive power changes. We can see here, and according to the Turkish standards, we must take into the consideration EK division delay rate, and according to this rate, we can use this table for limit values. When we look at the experimental results, especially in the melting process and especially in charge and boring process, we can see that harmonic values very high, and in refining process we can see is a stable manner. And when we look at the harmonic values, second harmonic is bigger than standards, and third harmonics sometimes bigger than standards, and when we look at the other harmonics, fourth harmonics bigger than standards. Generally, we can see that even harmonics, odd harmonics is bigger than standards, and total harmonic distortion always bigger than standards. And when we look at the literature, some researchers said that we can look to this rate and we can decide is arc furnace is will be flicker effect or not, caused by flicker effect or not. Some researchers say that this rate more than 18, and some researchers then this rate can be accepted at 15. But our arc furnace load, we can see that this rate very high, this ratio, and in this manner we can think that it's good for us, and we will not see flicker effect. But when we look to result, it's not true. Short time flicker effect, long time flicker effect, when we look to short time and long time flicker effect, we are seeing that spatially charging, boring and melting period, short time flicker effect is bigger than standards. But if I accept the ratio, it's not be occur. But long-term flicker effect too higher than standards. And we experimentally look at the melting and boring and refining periods. We can see here frequency analysis. This always total harmonic distortion always very high, and we can see in stable manner in the refining period. We see that harmonic is especially even harmonics is very high, but we cannot say this harmonics because of occurring because of electric arc furnace. So that I modeled this circuit, and it is including my SVC system for compensation and harmonic filter groups, and I give it 1 ampere current, And we used this circuit because I want to see how is changing in the utility side the harmonic effect. And when look at it, I see that nearly second harmonics and nearly fourth harmonics, and between this area harmonic current is hiding. And if we can say that if more than third harmonics values because of the electric arc furnace load, and in this harmonics because of the SVC systems, because harmonic filter is enough for the filtering the system. And how we can reduce the disharmonics? First, even harmonics is a problem for us, and we must reduce disharmonics. For that, we can reduce the transformer power for arc furnace, but it will be not good possible for us, because arc furnace load will have some production losses. The second solution, increasing the short circuit power of the grid. If we increase the short circuit power, this ratio will be big, and we can reduce the even harmonics, but this is including the Turkish electricity distribution company, and it's very high cost, so that we don't offer this solution. And another solution offer reducing the current of electrical arc. It's generally application, but we are offering this application for big furnace, because 16 MVA furnace we are investigated, and if I reducing the arc current, firstly my furnace not will work very well, and production will be reduced. And second, for that I must to add the system and serial reactor. And when I add the serial reactor, I will reduce the disharmonic, but when we compare the first station, the nearly second harmonic values is bigger than before. And it is not good solution for small arc furnace. 16 MVA arc furnace, when we compare the other arc furnace, 16 MVA arc furnace little small. And small arc furnace, for small arc furnace, this application not good. And other solutions, instead of the three-star controller reactor and static var compensation system can be used for the existing system for harmonic filter, because analyses show that SVC systems cause to second harmonic values, and third, we can say even harmonic values. As a result, we can say that power quality problems are mostly seen and boring process of electrical arc furnace, and high current values occurring to this process. Existing SVC system is not available for electric arc furnace application because SVC systems, we are see that experimentally SVC system caused by even harmonics, and even harmonics is problem for us. We are suggest that according to the SVC systems, three-stir control reactor or static compensation, STATCOM systems, we are offering to for these systems. And we can say that when we compare with literature, even if the ratio of short circuit power at the common connection point, this ratio is more than 18, flicker effect can be observed, and we can say that we cannot make the assumption like that, because if I accepted this assumption, it will be not true. And we are say that second harmonic and third harmonic, even harmonic, will be problem for us, and this result must be taken into consideration for electrical arc furnace. Thank you so much.
Now, questions, please.
Just one question. You said that you face the problems with the second and other even harmonics. From my experience, those harmonics typically appear when we have asymmetric load or when we have a DC component.
Yes.
So have you checked eventually about those effects? Or you are sure that your even harmonics are coming from the other side?
Yes. I can see here, come back, and I modeled this circuit, and I give it the 1 ampere current here. And when I make it my aim, and how will be changed in the network side. And when we look at these results, we can see this graph. And this graph shows that it's now arc furnace load not including the systems. And without the electrical arc, if we find these graphs, we can say that if I see another harmonics here, this caused by the electric arc furnace. But in this manner, not including the system arc furnace load, and I can say that I don't have any load, and I am checking my SVC system and harmonic filter performance, and we can see here even harmonic is a big problem, and my harmonic filters is modeled very well. As a result, I can say that this is result of SVC system only.
Thank you.
Thank you.
More questions? If not, we will proceed to our last. Thank you.
Thank you.
Once more. And we will proceed to our last presentation, that will be two-stage data fusion of acoustic, electric and vibration signals for diagnosing faults in induction motors. It will be presented by Anna Steve from Poland.
Good Good afternoon, everyone. My name is Anna Stif. I'm from Hungary. Currently, I'm working in Poland in the ABB Corporate Research Center Krakow. My paper title is Two-Stage Data Fusion of Acoustic, Electric and Vibration Signal for Diagnosing Faults in Induction Motors. So basically, this topic is connected to condition monitoring of induction motors. Here is my agenda. I will give a short introduction with a little background and what is the motivation of this work. Then I will talk about the case study and data acquisition. Then a little bit about the methods. I will show you my results and then I will conclude. So let's start with the introduction. There is increasing demand for condition-based and predictive maintenance. This need is for early-stage fault diagnosis, which is really important to avoid costly and serious failures, accidents, and also costly maintenance activities. Each condition monitoring approach has its strengths and weaknesses. There is no single approach which is able to diagnose all types of faults. The question is why to fuse data from different sensors. In case of fusing data from different sensors, these sensors can cover a wider range of diagnosable faults. There will be an effective distinction between faults. Also, it yields reduced false alarms and reduced missed alarms. False alarms are in those cases when the system or equipment is actually healthy, but the algorithm or the condition monitoring system thinks that there is a fault there, and the maintenance personnel comes and they notice that there is no fault and they had to stop the production, so it's also a problem. In case of missed alarms, the situation is the opposite. The system is healthy, but there is a fault, and because of that fault, there might be a stoppage in the production or in the system also. So, fusing data from different sensors, for example, from vibration, magnetic, acoustic, electric, OLW or pressure sensors, can give a more complete picture on the system, and it can increase the accuracy of the fault detection. So the aim of this paper is to show that fusing different sensor data can give more reliable and robust condition assessment. Our starting point was work done by Jaramillo et al. He took a system which composed of different components, and he fused this component data on the local level, and then the diagnostic results of the local level were fused at the global level, and the results of diagnostics improved. Our thought was to use this approach for combining sensor data, different sensor data. For example, there is a system, there are different sensors. In our case, it was vibration, acoustic, and electric sensor data. We do the feature extraction, and on the local fusion, there is a prediction of health state already, and this health state is used on the global level, which improves the, we show that improves the results of diagnostics. So our system looked like this. There was a motor with a load, and there were 5 different types of sensors. The motor had actually, there were 4 identical induction motors, but with different health conditions. There was one motor which was healthy, one had 2 broken rotor bars, one has 3 broken rotor bars, and one had a bearing fault. And these are the signal types that we were collecting: microphone, current, vibration, and voltage. If you are not familiar with microphone, it's a 3D sound intensity sensor, which is measuring the acoustic particle velocity. Here is a picture of our measurement setup. The measurement was done at the Krakow University of Technology. So, what are the methods? For the feature extraction, we considered time domain and frequency domain features. For the time domain features, we took the usual statistical features, the root mean square, skewness, kurtosis, maximum peak-to-peak value, and the crest factor. And for the frequency domain features, we selected amplitudes as given frequencies. The first three harmonics of the supply frequency, the first three harmonics of the rotation speed, the sidebands of the rotation speed, and sum of the ratio of these amplitudes, also with the frequency center and spectrum area. Now that we extracted the features, we had to calculate the threshold level to determine if it's healthy or not. We calculated the threshold using the kernel density estimate. This method is especially useful in case that there are random variables with unknown prior distribution, which was in our case. We set the thresholds at the upper limit of the 95% confidence interval. Also, our motors were recorded under 5 different loading conditions, and we observed that the load, that the features are highly dependent on the load. So we had to consider this when setting the thresholds. We made a first order polynomial load model for the thresholds. Our method was Bayesian inference, which is based on the Bayes theorem. A very simplified way of explaining that there is some prior knowledge, we have some local likelihood functions, and based on that we can make a decision. For example, we know that the weather forecast today is a little bit sunny, a little bit cloudy. We see some clouds, and based on our previous experience, we know that we might need an umbrella. We applied this theorem in the following meaning: the probability that the fault Fi occurred in the system, given that the feature crosses its threshold, is updated according to the Bayes theorem. This approach was used at the local level and also at the global level. Here is again the structure of our algorithm. The vibration, acoustic, and electric signals were gone under feature extraction. Then for the signal type separately, this Bayesian inference was done, and this gave already probability of the chances of the faults for the 4 motors. These results were then combined in the global level, and this was our result of diagnostics. So I will show you some results. These are the results of the current signal after the local stage. In the rows you can see the actual condition, in the columns you can see the diagnosed condition, and our aim is to maximize the values in the diagonal, which are the correct guesses. As you can see, F1 is healthy motor. In case of healthy motor, the success rate was 63% only in the cases, and there was a 37% of false alarms when the algorithm on the local stage saw that the motor is actually with 3 broken rotor bars. Similarly, in case of F2, which is motor with 2 broken rotor bars, the algorithm had 3% of missed alarms when it saw that the motor is actually healthy. There was also misclassification of fault. Instead of fault 3, the algorithm calculated fault 4. So when we look at all the 5 signals, you can see that none of them is really perfect, although the vibration signals are the best and the voltage signals are the worst. But when we look at the few signals, you can see that the accuracy significantly improves. It's 99% of accuracy diagnosing healthy, and even the rest are very increased compared to the previous result. If we look at the confusion matrix of true positive, false negative, false positive, and true negatives, you can see that these are the false alarms. It was reduced to 1%, and the missed alarms, it's only 1.37%. So, what are the conclusions? With our method, fusing different sensor data and the local and the global stage with the Bayesian method, we managed to reduce the missed and false alarm rate. We improved the accuracy of the fault detection and increased the reliability and accuracy of the method. Although we have some limitations here, this method is only useful for steady state signals, and there is no distinction between false severities. Also, it depends, as it's data-driven approach, it depends on the quality of the training data. So that's it. Thank you for your attention. Do you have any questions?
Thank you for a very nice presentation. And now is the time for questions. Please.
I guess that ABB and commercial companies, you search for some trade-off between cost and reliability.
Yeah.
Because I guess that number of the sensors increase the cost of the equipment and so on. So I haven't got in your presentation or in your approach any searching for trade-off between reliability and the cost. Do you have this consideration in your project?
In this paper, I didn't consider this one, but yes, in the Pronto project, we have a work package on that, how to optimize this cost of condition monitoring and the reliability trade-off.
Because you didn't take under consideration neither the reliability of sensors, because they can be broken too.
Yeah, of
my
course.
car always stopped because sensor was broken, so this could be okay. Very nice presentation.
Some more questions, please. Yeah.
Okay, is this work implemented probably offline on some computers? Is it possible to implement it on, for example, microcontroller which is used to control the motor, so it would be standalone solution?
Yeah, that would be a nice idea for future work. For now, it's not implemented yet.
More questions? Yeah. I would like to ask some more. Is it possible that these all sensors are integrated inside your model, or I see like these microphones are from some distance away? It's not very comfortable to collect this data in real situation. Can it be integrated
in this case, it was a laboratory experiment, but there are some solutions when the sensors are integrated and the condition monitoring is done online.
And in case of bigger models, it is not a big expense, of course, because big models are also very expensive.
Yeah.
Thank you very much.
Thank you.
And now it's my pleasure to close the session because all the presentations are done. And I thank you for listening and the presenters for presenting all these papers, our presentations. And I guess that we meet again soon. And now, after some 45 minutes, we will leave to this dinner, and buses will be probably in front of the hotel. Yeah. Thank you very much.